Okay, so 12.1 is called Visual Displays of Data. So this is like our introduction into the statistics chapter. Chapter 12, we're going to be doing lots of different statistics. We're going to be looking at lots of different variations, and we're going to talk about frequency and distribution and normal distribution and mean, median, and mode and all kinds of stuff. Some of it you've probably encountered in previous math classes. Some of it may be brand new. One thing that I find pretty interesting about tackling Chapter 12 in this year is that it is applicable because we are entering into an election year where we deal with a ton of statistics. There are a ton of population and sample sizes and things like that, where they tell you who's going to win the election and who's not, or who's going to get the delegates here, here, here. All of that is statistics. And one of the big thing that we like students to walk away from the statistics section is distrust. You should always question any statistic you read anywhere. If they tell you that drinking 2 glasses of wine a day is healthy for people, you should look what kind of people are they actually interviewing for this. A lot of times when you read the reports and read who the sample population was part of this report, it's a very small population, and it's like 2 glasses of wine was really good for Asian American women between the ages of 30 and 40. And it's like, so if you're not an Asian American woman between the ages of 30 and 40, then this statistic really doesn't apply to you. And when we think about like upcoming elections and things like that, when they tell you that they're projecting that 70% of Missouri is going to go Republican or Democrat, they didn't poll 70% of Missouri. They polled a couple of different places and are taking that data and extrapolating it. And if you think about who actually goes to the polls before the main election, it's mostly the really old because they have the time to get to the polls, and so everything is skewed based on generations. And so anytime you read a statistic, you always need to ask, where is this coming from? What is the sample population that's actually being asked? Because the statistic is going to differ greatly between where they get their information. We can see that even across campus, and even with something as simple as your favorite lunch food or your favorite class or your favorite whatever. Like anytime you poll a set of students, it's going to be completely different based on, well, if I'm polling you guys at 8 o'clock in the morning versus a 9 o'clock at night p.m. class on whether or not you enjoyed the class, well, if you're a night owl and you're in my 9 o'clock class at night, you're going to love it. If you're a night owl and you had to take my 8 a.m. class, you probably hated it. You know what I mean? And so always question, what is the population and where are they getting their information? That's a big thing. So I've said the term population a couple of times. Population is all of the items of interest. And so in an election year, the population is the population of America. Or usually they actually even limit it back down a little bit, where it's not all of the adults over 18, it's all of the eligible voters, because that's even a subgroup of the adults of America. But the population is all of the items of interest, and then your sample population or your sample size is just some, usually not all, of the items in the population. It's not feasible to go door to door and ask every American who they're going to vote for. It just doesn't work that way. And so that's why they use these little groups, these little sample populations, and depending on where you get those, your answers can be very skewed. One thing that I wanted to kind of draw your attention to, because maybe this box and circle of population and sample looks a little bit familiar, your population is a lot like your universal set that we had back in Chapter 2. I should write set next to that. Your universal set was the big main set, and then we had subsets within our universal set. That was our set A and our set B, our smaller sets. So that's what the sample is. It's a subset of the universal set. So even though we're going to talk about statistics, it really ties back with some of the stuff we did in Chapter 2. Now, you're not going to be asked to give the subset of anything or anything like that, but the general concept of what a population is versus what a sample is very much the universal set versus a subset. Some of your homework problems are going to be what we call conceptual problems, where they ask you questions and they're true or false based on some of the definitions, like of what a population is or what a sample set is, and things like that. All right, so there's two main areas of study in statistics. There's descriptive statistics. That's where you collect, organize, summarize, and present all of your data or your information. In short, this is your describing, thus it's descriptive, of the data. These can apply to the populations or to the samples themselves. Inferential statistics consist of drawing conclusions, making inferences about the population based on the information from the samples taken. And so we can infer, which isn't always safe, but you can make some inferences or assumptions of a population based on what they give you as information. And so one of the problems that I liked is I liked this one where it was a bunch of marbles, but again, looking at them in black and white isn't very helpful because you can't see the colors. So again, I've scanned in the color version, so you can access that on Blackboard. But here we have a population of 10,000 marbles, and they're red, white, and black and green. There are some black in there. So when you look at 10,000 of them together like that, it's really hard to make any inferences at all. I can say there's a lot of different colors, but I can't tell you which one's more dominating. I mean, part of me wants to say white, but then there's also this ring of maybe it's black or maybe it's just, a shadow. Like, it's hard to really make some conclusions when I'm looking at 10,000 different pieces of information. So if I take a random sample of 25, which is what this board shows me here in the middle, I can actually then look and make some inferences or make some conclusions based on this information. And for this problem, or for this discussion right here, we're going to look at green marbles. So if I look here at the green marbles, I can't tell you anything really about it. I can say there are green marbles. I can't tell you how many. I can't tell you if that's the dominating color or not. All I can tell you is there are some green marbles. So if I look here, though, and I know that there's 25 total population, I can count my green marbles. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 25 are green. And if you type that into your calculator, that's telling you that 36% of the marbles are green. We can make then a general assumption that, okay, well, if there's 36% green here, I could say maybe there's 36% green there, but that's kind of a stretch because 25 is a pretty small sample size when you think about that we started with 10,000. The larger the sample size, the more accurate your inferences or your descriptive statistics will end up being. So even if we move over to the next paddle, this next paddle has 100. So we just quadruple sized our random sample. And so if we go through and count them, which you don't have to do, but if you were to count all of the green marbles here, we would have 28. Again, this is a random sampling. We just scooped out a bunch of marbles and filled up the board. But we would have 28 out of 100, which means 28% are green. Well, those are very different statistics. I went from, I have no idea how many are green, there's just some there, to 36% are green, to 28% are green. The bigger your sample size, the larger, the better representative you're going to have. And so this is how come when you watch the news during an election year, Fox may say that 36% of a state is going to go red, whereas CNN may say that 28% is going to go red. It's because they're dealing with different samples, they're dealing with different sets of data. The better information is going to come from your larger samples. Okay. I started to color this one in, and I'm like, you're never going to be able to tell which ones are which here, so that's why I went back to the colored version. And if you wanted to add an extra note, larger samples give a better representation of the entire population. Like if I pulled you guys today, sorry, that's a little bit off. It says representation. Like if I pulled the class today and I said, what's your favorite breakfast food? There's 15 of you in here. and you guys, the majority says Pop-Tarts. I don't know. I could say the majority of mathematics students at Missouri Southern want Pop-Tarts for breakfast. That's not a very good representation of the math students at Missouri Southern because I pulled one class out of all of the classes that are being taught. I took a sample of 15 out of a population of like 700 students. Not a good representation. If I wanted an accurate picture of what the preferred breakfast food was for all math students, I would have all of my professors ask that question during their math classes, and even then we still wouldn't get 100% participation because people would be gone or choose not to participate and things like that. But the larger the sample, the better assumption or overarching swipe I can make basically in my information that I want to present. So let's have some definitions. I told you there's not a lot of actual computational math today. That's why I made a handout. All right, raw data is the data that's been collected but not yet been organized or processed. Our population of 10,000 marbles here, that's kind of like your raw data. We haven't done anything with it. You can have quantitative data. Quantitative, notice it starts like the quantity, so numerical data. That's our numbers. The non-numerical data is known as qualitative. Kind of looks like quality. So the qualitative data is that we have different colors of marbles, and we could list the different colors of marbles. Quantitative is actually computing the percentages that we would have, or stating how many of each marble we have. Now, the first style of problem, and the one that we spend most of our time and your homework and such on, is frequency distribution. So when a data set includes many repeated items, it can be organized into frequency distribution, which lists only the distinct data values X along with their frequency. So if I was polling the class about breakfast food, I bet you some of you would have the same favorite breakfast food. More than one of you would pick Pop-Tarts or whatever. I could make a frequency distribution table off of how many of you chose Pop-Tarts, or how many of you chose cereal or eggs or whatever. And then we could take it even a step further where we look at the relative frequency. That's the fraction or the percent of the data set represented by an item. So if N denotes the total number of items, so you guys are the total number of students that I'm questioning. So that would be the N. And then X is the item, is the given item, so Pop-Tarts. Occurs F amount of times. Then we can use the relative frequency of putting the number of you that chose Pop-Tarts over the total number of you, and that tells me a percentage of how many picked Pop-Tarts. Okay? That's what relative frequency is. You guys actually use this and everything. One of the things that's nice about Chapter 12 is a lot of you, depending on your majors, have a specific statistics course within your major. Business has a statistics course. Psychology has a statistics course. I don't think biology and them do. I think they use our statistics courses. But a lot of the degrees on campus have a specialized statistics course that's tailored for that degree. And all of this stuff will be applied and worked out in those classes just in more detail in terms of, you know, when you take a experiment in psychology and you're taking all this data, how are we going to represent that to where it actually makes sense and teaches other people what it is we found out. So you do use this stuff in your major, I promise. But relative frequency and frequency distribution is going to be something that we do a lot of. Oh, I did leave it blank. I wasn't sure if I did. So this is a style of problem you would see. It says 25 members of a psychology class were polled about the number of siblings in their individual families. We're going to construct a frequency distribution, and usually when you see that, it's kind of, you can imply the word table. We usually label it with a table. And then we're going to use relative frequency distribution for the responses. So 25 people are asked how many siblings do they have, and these are their responses. Notice we have a lot of them that repeat. There's more than 1, 2. There's more than 1, 1, and so on and so forth. So having this string of data doesn't really help us understand, you know, do the majority of the classmates have 2 siblings or 4 siblings? We don't really know. So we're going to make a table. we're going to make a frequency and relative frequency distribution table. I'm going to make one table to hold both of the answers. I noticed on Pearson, that's how they usually give it to you as well, and so I think that's a pretty good way to start it. So we're going to start with the number of siblings. That's our X. And if I look through here, I have 1, 2, 3, 4, 5, and 6. Those are all the different numbers that I have. So some people had 1 sibling, some had 2. Our next column will be the frequency. Frequency is how often did that number show up. And then our last column will be our relative frequency. That's where we take our frequency compared to the total. And this will be given as a fraction or a percentage. And Pearson will tell you which form they want you to put in. So then we're going to go through and we're going to look. Okay, I have 1, 2, 3, 4 ones. 1, 2, 3, 4, 5, 6, 7 twos. 6 threes. 1, 2, 3, 3 fours. 3 fives and 2 sixes. And I'm going to remember that I had a total of 25 participants. I mean, I could add up that column right there of frequencies, and I would know that I had 25. Sorry, there you go. But they told us they asked 25 different students in the psychology class. So the frequency is right there. So we can see based on that column of our table that the highest frequency fell to 2 siblings and 3 siblings. 7 people had 2 siblings, 6 people had 3 siblings. So now we're going to compare that to the overall class to kind of see the percentage breakdown. So what we do is we take our frequency, which was 4, and we put it over the total number of people in the class, which is 25. So if you have to do it fractionally, that's what you would put. If you have to do a percentage, that's 16%. And we're going to do that for everything going down. So 7 over 25, 6 over 25, 3 over 25, 3 over 25, and 2 over 25. By coming up with a relative frequency, we can draw some bigger conclusions, or we can talk about it more in mathematical or quantitative discussions. We can say almost a quarter of that class had 3 siblings, because 24% had the 3 siblings. A little bit more than a quarter of the class had 28 siblings, and we can draw some conclusions, or we can talk about our data a little bit more in a mathematical way. But you do this in business too. If you want to open a business and you're trying to figure out what to sell, you're going to want to poll your potential buyer, because you want to make sure that you have a product that's actually going to sell. And if you want to sell chocolate cupcakes, but the majority of the people in the population you're going to target want vanilla, then it's probably not a wise choice for you to sell only chocolate cupcakes. You probably want to market yourself towards what is actually going to be profitable for your business. Statistics are everywhere. They really are. So a lot of your homework is doing this, where you make a frequency table and you make a relative frequency based on the total population. Now, in your book, they also give you what's known as a histogram or a frequency polygon. Those are images, and I'm going to show them to you. You are not going to be asked to present, actually make them. But I do include them. And since I need to look online and make sure that I have this version scanned in, because I want to make sure I have the answer key version scanned in as well as the blank one. But a histogram is just where we're going to use, it's like a bar graph, where we compare the number of siblings versus the frequency that we have them. Notice on a histogram there's numbers on both sides. That's important just because it comes up in one of your conceptual questions. So I wanted to make sure and really point that out to you. But this is kind of a quick way for us to look through and say, okay, well, I know that the highest frequency had 2 and 3 siblings, and it's just another way to represent the same information. A frequency polygon, again, represents the exact same information. And if you look at it compared to the histogram, we have the number of siblings on the x-axis, we have the frequency on the y-axis. It's just this one we're using like a line graph. And it makes this kind of wonky shape, this polygon, which is why it's called a frequency polygon. The table, the histogram, the polygon, they all show the exact same information, just in different formats. Nothing has changed. It's all the same. Flipping through your Pearson, it looked like you guys used the tables. So that's why we're not going to draw the histogram. You're not going to be asked to do that. But you should be able to look at a histogram or a frequency polygon and be able to ask answer a couple questions about, where's the highest frequency, or the number of siblings at 5, how many had that, or can we draw that assumption, and so on and so forth. Okay. Are there any questions about how you make a frequency or relative frequency table? Okay. Let's talk about grouped frequency. I'll zoom out a little bit. Nope, that's in. Because I did put a little note on top of it. And I'll read that. But grouped frequency distribution is where you have a data set that contains a large number of items. So the larger your data set, the more complicated it is to actually draw conclusions and talk about them. So a lot of times what we do is we will group our items together into different groups or classes. And I've got a couple of real-life examples to talk about whenever we get through this little bit. For the first problem, that frequency one that we just did, we didn't actually group anything. There was only 6 options. It was 1, 2, 3, 4, 5, and 6 were the number of siblings. And we just kind of made a list of how many had each of those siblings. We didn't need to group them. There was only 25 pieces of data. It wasn't super hard. But when we're talking about 10,000 things, or even 50 or 100, that's a lot more to talk about. And if it ranges from the number 1 to the number 78, that's a lot more information, and there's a lot more that we have to consider. So when we group frequencies, that will help us. So here are some guidelines for when you're grouping. The first thing you want to do is you want to make sure that each of your data items will fit into one and only one class. They can't go into both. So if I'm going to do a group frequency based on the ages in this room, I need to make sure that I'm going to have the age range from 18 to 20, 21 to 22, 22 to 24, and things like that. Not I have 18 to 20 and then 19 to 21, and where you could be categorized in multiple different things. You need to fit in one place and one place only. The next thing you want to do is try and make all your classes the same width. So if we're talking about the ages within this classroom, I'm not going to do 18 to 20 and then 20 to 25 and then 25 to 45. Those are different widths. That first width only had 2 years, and then I had 5 years, and then I had 20 years. That doesn't give us a good representation of what's happening with our group frequencies. If I start with 2 years as my gaps, I need to make it 2 years all the way across to cover all of our ages. Step 3 kind of is the same one as step 1. You make sure the classes don't overlap, because if the classes overlap, then obviously something could fit into more than one class. And it says usually you want to use 5 to 12 classes. If you use less than that or too many classes, then it can obscure your tendencies and your data. So these are good rules to go by. And we're going to see some examples. So here we went up to a population size of 40, because 40 students are going to be randomly selected in a school cafeteria one morning, and they're asked to estimate the number of hours that they spend studying in the past week. And that includes both their in-class hours and their out-of-class hours. And then we just have this listing of data. We have 18, 60, 72, 58, blah, blah, blah. These are the number of hours these students studied. So we need to tabulate a grouped frequency distribution and a grouped relative frequency distribution and construct a histogram and a frequency polygon. Again, you're not going to do the histogram and the frequency polygon. I'm going to show them to you. What we are going to do is we're going to do the grouped frequency and relative frequency distribution table. So if I'm looking at this data, let's see, 12. I'm trying to look for the smallest and the largest piece. I go from 12 all the way up to, I don't know, what's the largest thing? 72? So that's a pretty big range if I'm thinking about making, like, I don't want to make a frequency table based on all of these numbers between 12 and 72, because most of them are not repeated more than once. So what I'm going to do is I'm going to break down and make my classes. So I'm going to make class limits. And I know I start at 12 and I go to 72. But what I'm really going to consider is like 10 to 19. I'm going to take these subcategories of 10 numbers at a time. So I'm going to do the teens. Then I'm going to do the 20s and the 30s and the 40s. When you apply for a job or you like applied to college, I know you had to like indicate your age range. And some of that's for statistical purposes where they're trying to look at the average age of a college student and, you know, when are students coming to college, when are they not, do students come back to college. One real life one that popped in my head when I was looking over these notes is if you've ever done a race, like a 5K or even a fun run or anything like that, they will break down your age into age categories. And usually it's something like this, where it's 10 to 19 is an age category. You'll have like an overall winner and things like that. Or 20 to 29. So that was one that came to me. Or even if you want to think about it not with numbers, think about if you watch the Oscars or the Academy Awards, they break the movies down into different genres. And then you have, you know, the best leading actor in a horror flick or the best leading actor in a comedy. We don't usually compare them together. I could be completely wrong on that because I haven't watched those in a long time. But you can break down movies based on their genres or books based on genres, and then you can do some comparing that way. Okay, next we're going to do frequency. And then we're going to do relative frequency. So the only thing different that we did here is we are considering a group of information instead of just a single data piece. So with our previous class of 25 students, there was only 6 options, so we literally just had 6 things. We didn't have to group them together. Here, we're grouping them together because our data ranges from 12 to 72. And so when we're doing frequency, there's a couple different ways you can do it. You can go through the main list and just look for all your teens and look for all your 20s and 30s and 40s and so on. You can also do the one that's in the actual book. They just do a tally mark system. You can do that as well. But we don't really look at the tally mark system afterwards. That's why I left it off of our table, because we just use the frequency column. So I'm going to just go through and make little slash marks over the numbers. We have 1, 2, 3, 4, 5, 6 teens. Then we're going to do that for all the numbers. So 1, 2, 3, 4, 5, 6, 7, 8. I feel like I'm missing one. According to my tally, I'm missing one, so 1, 2, 3, 4, 5, 6, 7, 8. Do you guys only get 8 20s? Ah, there it is. Thank you. was like, I'm missing one. Can't find it. All right, 30s. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Lots of 30s. 1, 2, 3, 4, 5, 6, 40s. 1, 2, 4 50s, 1, 2 60s, and 1 70. And we know our total in this case was 40. One, you could add up all your frequencies, but also they told you that they asked 40 students. So we need that total in order to do the relative frequency. And something that's a little bit different with relative frequency is oftentimes we do not simplify it if we have to leave it in a fractional form. Because if we simplify it, like with this first one, it'd be 6 over 40, which is not a simplified fraction. But if we simplify it, then we forget what the actual total was of our population size. And so a lot of times we will just end up leaving it as a non-simplified fraction because then I can say 6 out of 40. Or if they want the percentage, it's 15%. 9 out of 40, studied 20 to 29 hours. That's 22.5%. 12 out of 40 is 30%. 6 out of 40, again, is 15. 4 out of 40 is 10. 2 out of 40, 40. It's 5. 1 out of 40 is 2.5. And remember that this was the information of how many hours a week these students studied. We could go further in investigating this, and we could compare the number of hours that the students study versus their grade point average. And then we could make some inferential assumptions from that. We could say, well, it does seem that the majority of students who spend, maybe not the most studying time down here in the 70s, but we might find that 40 to 59% of the students have the highest GPA out of all. So this is like the sweet spot or the sweet area of studying. There does get to be a point where you've studied too much and your brain's oversaturated and nothing absorbs. And so that's probably down on the other ends. So you can make some inferential information if we have some more data from this. Let me show you the histogram. The histogram, again, is the exact same information. It's just using bar graphs to represent the frequency. We have the number of study hours and the frequency over here. If you have a group frequency polygon, again, same information as all the rest of it. It's just what does the polygon look like if we do a line graph with this. And then this one was just a smaller subgrouping of the grouped frequencies without the relative frequency. Are there any questions on how we do the groups? Could we have structured our groups differently and gotten different information? Sure. We could have done the class size and had 20 hours as our sub thing. But then we would have had under 5, and so that's why we went with a grouping of 10 hours in each category. I'm trying to think if I actually saw any grouped frequency ones on there where they didn't go ahead and break up the class sizes for you. I feel like they go ahead and give you those. And then you just have to fill in the frequency and the relative frequency aspects. Any questions? All right, let's look at stem and leaf. And actually, I'm going to just show you stem and leaf because I was told downstairs it's not super important. So we're going to look at it and we're going to talk about it. Because you do have to fill in a stem and leaf. When you fill in a stem and leaf, what will happen is you will be given something like the yellow box with this category blank and with all of this blank. And I'm going to tell you how you get all this information, because it says present the study times data from the previous example as a stem and leaf. And so that's this data, this table, that all these information, these study hours, are represented in that stem and leaf. And here's how it works. Stem and leaf is where the stem is the first number in your data. So if I'm looking at the number of hours that these kids studied, they studied anywhere from 12 hours to 72, we saw. So we have the tens place of 1, 2, 3, 4, 5, 6, and 7 is what we have. Those are our stems. And off of our stems are going to grow our leaves. I think it sounds kind of weird, but... So I'm trying to leave some of the information up there at the same time. So like if we look at stem 1, that's where we list all of the leaves that have a tens place of 1. And they went in order. So they went across the row. And the first one was 18. So 8 is listed as the first leaf. And I don't believe the order matters as long as you represent all the data. Okay? So if you went down the columns and it was in a different order, it wouldn't matter. But 8 is our first leaf, and then I go across and I have a 15. So 5 is my next leaf, and I go next door, and 2 is the next leaf, and then 6, and then 4 is somewhere else, and so on and so forth. And I do that for every single one. So all of my data pieces in a stem and leaf are represented. Whereas with our table, with our frequency and the grouped things, we just know that 6 of them lie between 10 and 19. We don't actually know what those values are. We don't know if they're all 10. We don't know if they're all 19. We don't know what they are. We just know that 10 different students studied between 10 and 19 hours. With a stem and leaf, I can say, well, one student studied 18, and so on and so forth. And so stem and leaf gives you more detailed information about the individuals within a group. It still groups them, you'll notice, because we still have our teens, our 20s, our 30s, our 40s, and so on. But I know each of their individual amounts. And that will help us later on when we are looking for mean, median, and mode, and we're trying to actually group and organize them in a specific format. So stem and leaf is nice. It just gives you more information, but you are still dealing with groups. It's just here we're kind of looking at bigger pictures of groups. Stem and leaf, we can actually look at the individual within each group. Okay. Bar graphs, circle graphs, and line graphs. For these, it's really more about learning how to read a graph than actually producing the graph. And so on Pearson, they give you the graphs, and then they will ask you questions about the graph, which is how this problem works as well. It gives you a lot of information, and we're going to answer some questions. So it says in a 2017 study by Swiss researchers, they predicted a worldwide 2030 baseline of 200,000 tons of antibiotics used in food animals, with possible reductions if one or more of the following strategies were applied. So basically what that just said is that if there's nothing applied, that by the year 2030, there's going to be 200,000 tons of antibiotics pumped into our foods that we eat. That's what they're finding out. But they know that there's 3 strategies they could try to eliminate or reduce the number of antibiotics. One of them is capping. They want to cap the amount and use only 50 milligrams per kilogram of animal product. So if you limit the amount of antibiotics you put into an animal, that would help reduce the overall antibiotics. Then there's reducing the consumption of meat to 156 grams per day per person. So if we limit the amount of meat we eat, then obviously we're limiting the amount of antibiotics that we take in from the animal source. The other one is imposing a 50% tax on those antibiotics. If we make the antibiotics more expensive, then the meat companies won't want to use them because then it inflates their product price and then people won't buy it, all that kind of stuff. So they made this table, this nice bar graph for us. And it says to the nearest percentage, we're going to figure out some stuff. We're going to figure out how much reduction is predicted under each of the following conditions. And so we see here we have the different types of interventions on the left-hand side and the estimated global antibiotic use in 2030 based on 1,000 tons along the bottom. And it said in the very first sentence that they predict by the year 2030 there's going to be 200,000 tons of antibiotics if we do nothing. So that's what this black one is. It says no intervention, and that has 200,000 tons of antibiotics. And we see they're predicting that if we use the capping, it's going to be down to 81 tons of antibiotics. If we use the reducing the consumption, it's at 157. If we do the tax, it's 138. And then they do some different combinations. If we combine the reducing and tax and so on and so forth, and we see that we have the biggest reduction in the use of antibiotics if we use all three. If we cap it, reduce the amount that people consume, and if we tax it, we're down to 40 tons of antibiotics. So our questions, though, are about these. What is the percentage of reduction if nothing is there's no strategy in place? So I hated the way it felt just on the paper. These are our questions, but the space to actually do the math is on the next page. So if you have your thing open, you can see both, but I'm also going to write up here, A is when none is taken, so that we know what we're doing. B is C only, C and T, C, R, and T. That way we know what we're actually looking for. And so they're asking us to refer to the bar graph, which I'm trying to leave all of the bar graph on there. And it says, to the nearest percent, what reduction is predicted under each of the following intervention strategies. And so what we're doing is we're going to take the starting amount, which is, if no interventions are taken, it's 200,000. So that is the starting amount we're going to have. And I'm just going to say 200 and keep it short. So if there's no interventions, we're going to subtract whatever the final is, which in this case is 200. This one looks a little bit weird because nothing's really going to happen in this case. And it's all over 200. That gives us a 0% reduction. Obviously, if we take no intervention steps, then nothing's going to get reduced. It's like saying, how do we lessen the amount of garbage that we put into landfills? Well, if we don't do anything, the amount of garbage we put in there is still going to be the same. There's no reduction. So what if we try capping, though? If we try capping, we take the 200 and we're going to subtract the 81 because that is the amount of reduction we're hoping to get out of it. And then we're going to divide that by the 200 because that's going to give us our percentage of reduction that's happening. So 200 minus 81, sorry, my math's on the other page, is 119 over 200, which means that there's approximately a 60% reduction. We could cut out 60% of the antibiotics just by capping. So what if we cap and tax? Do we have a bar on there for tax and capping? No. We do not. We have one for reducing and taxing or capping and reducing, but we don't have a bar graph up here that tells us what happens if we do both. So there's no data. There's not enough data. We can't make any conclusions because they don't give us the information. We can't say, well, it's 81 with the C and 138 because we don't know. We don't know when we combine those two things what kind of reduction we're going to get, so we can't draw any conclusions. Now for CRT, we do have information. That's our bottom white bar, and it's 40. So we would take 200 minus 40 all over 200. That's 160 over 200, which is about 80%. If we did all three of the strategies, we could cut down the amount of antibiotics that is presented in the meat products that we eat by 80%. So when you're trying to read the graph and come up with a percentage, you take the whole, subtracting whatever it is you're considering, the population, and then you divide it by the whole in order to get the percentage itself. All right. We are going to stop there today.